Tessarotto.
Have you started?
He's from University of Trieste. He's going to talk about some application of genetic theory here, and I wish you enjoy it. Please.
Thank you very much. For the introduction. I want to show you a photograph I made yesterday on the bridge, Charles Bridge, and there is a sentence. I mean, the last words are what I'm interested in. This is in memory of a congregation which, you know, tells that this was done ab initio. I mean, from the start, they had this congregation. And what I'm going to do is to use an ab initio approach. An approach we start from the principles, and go to the consequences. Of course, science, physical sciences, go also primarily from the bottom up, namely from experiments to the principles. Okay, but sometimes we have to go from the principles to the consequences, and this is what we are going to do. Okay. Now, thank you very much. So my presentation deals with a particular subject, which I try to explain why I'm presenting. This is work with Claudio Tomaschini, which is not very recent one. I mean, the idea started in 2008. We were taking part in a conference in Kyoto, in Japan, and I was going to present a joint paper with Claudio. He was my student at the time. And we are going to present the second paper at the conference. The first one dealt with this subject. It was a mathematical physicist, French mathematical physicist. I can give you the references if you like. And a lady, and she, the name is Gatignol, and the lady was pointing out an open problem in statistical mechanics. And the open problem was precisely on this subject that I'm going to explain. So, and immediately with Claudio we started discussing, saying that probably the problem should be solvable. Instead, Professor Gatignol, the French lady, was telling us that this was not the case, it was an open problem, and so on. And basically, it concerned the property related to a famous kinetic equation proposed by Enskog in 1921, which is the Enskog kinetic equation. And now the Enskog kinetic equation is a phenomenological, is a model equation describing which should provide the statistical description of a hard sphere system. And this is a problem, starting from the principles, from ab initio. So this is our idea of our proposal to solve this problem, which I'm going to describe. Okay. This is a long story, but there are some also fund institutions, and this is a part of our investigation on we have in mind applications to environmental fluid dynamics also. Now, what is the motivation? The initial motivation of this problem is a very old motivation. Namely, it is the connection between the second principle of thermodynamics, the entropic principle, to statistical mechanics. Now, this link is still missing. I mean, at least rigorous missing. And the reason is that Originally, this problem was investigated by Boltzmann, Ludwig Boltzmann, the famous scientist, atomic physicist. In terms of Boltzmann kinetic equation. And Boltzmann formulated his famous Boltzmann H theorem, which I'm going to shortly to record. Now, but however, the interesting problem which remains to be solved, which is believed to be unsolved, at least in Dr. Cartignol, Professor Cartignol was stating this concept, that there are difficulties in extending the validity of the Boltzmann H theorem to the case of mixtures, namely the case in which you have ensembles of particles which differ by mass or other physical parameters, like size of the extended particles. If they are, for example, if we consider hard spheres, you might have a hard sphere with different diameter and mass. So different species, a mixture of different species. And this is related in particular to the Einstein kinetic equation, which I just mentioned. Anyway, the Einstein kinetic equation is a model equation which does not describe properly the dynamics of mixtures. So in the case of different species, this particular equation gives incorrect predictions. Okay, so in the past, been proposed modification, ad hoc modification of this equation, which, however, are not satisfactory because they are not based on first principles. They are not based on an ab initio approach. Okay. So, what we want to do, what I want to show, that actually it is not so difficult to prove the validity of the H theorem also for mixtures based on first principle, based on an ab initio approach. So, namely, starting from, not from the Einstein equation, but starting directly from the basic axioms of classical statistical mechanics. Okay, here we have some papers which are related to this problem. And in particular, there is a doctoral thesis at the bachelor degree level of a student in 2029, which this topic was discussed. Okay. Okay, now let me first start with the scheme. I will review briefly the statistical treatment of second principle based on due to Boltzmann, the axiomatic formulation of statistical mechanics, of microscopic description, statistical description in particular, and we will introduce the concept of statistical entropy, which is due to Boltzmann and Shannon. And then I will formulate first a constant H theorem, valid for n-body, it holds for the n-body statistical entropy, Boltzmann-Shannon entropy. Then I will show you this very elementary Blue-Lane lemma and formulate the weak H theorem in the case of like particles, and the same to be extended to the case of unlike particles, maybe mixtures. Okay. The starting point, as I said, is the contribution due to Boltzmann. First Boltzmann and also Einstein. But in any case, Boltzmann in 1872, 141 years ago, published his famous paper on the Boltzmann equation and Boltzmann H theorem. I must say that the work, this paper by Boltzmann, was not met initially with great enthusiasm by his contemporaries. In fact, there were a lot of criticism. In particular, the criticism arose because, let me see if I can. Okay. Okay. Went asleep. Anyway, the situation is the following: the work by Boltzmann met with some criticism, but with criticism from contemporaries because of two reasons. Because Boltzmann H-theorem violates two basic concepts of classical mechanics, two basic theorems. One is the Poincaré recurrence theorem. And the second one is the property of reversibility of the classical dynamical system. Boltzmann considered as the classical system, dynamical system, formed by n hard spheres, smooth hard spheres. The dynamics of this system is not only deterministic, but also reversible. And if you reverse the velocities of all the particles, and you reverse the sign of time, the solution will be remain invariant. This is a time reversal property. Time reversal symbol. The property of Poincaré invariance instead is somewhat more complicated. It tells us that if you consider the phase-space trajectory of the system on the constant energy surface, the same trajectory will approach almost any state, any point on this hypersurface. So this is the Poincaré recurrence theorem, which was already known at the time of publication of the Boltzmann article. Now, the reason why the paper by Boltzmann seems to contradict these two statements in that it predicts a reversible behavior, a macroscopically reversible behavior. So the underlying dynamical system is now called Boltzmann-Sinai because Sinai is the scientist who in the 60s, last century, discovered a fundamental property to be satisfied by this dynamical system. Namely, this system is also ergodic. So this, we know very, very well the mathematical properties of this dynamical system. It is even a satisfied ergodic property. And I'm not going to detail, but if you want, we can discuss later on what is ergodicity. But you certainly know what it is. Now, okay, so we know the mathematical properties of this underlying dynamical system. And now we should be able to afford a serious investigation of we should be able to understand better what is contribution of Boltzmann and Expo now, really the paper by Boltzmann is extremely difficult to understand, even now. But I say, we should try, and I think we can afford this to understand. But the point is that the description which Boltzmann used is an asymptotic description. Namely, he considered a very large number of particles, infinite number of particles, which means that he considers really what is called an infinite dynamical system, infinite dimension. And then the diameter of the sphere, the arc spheres, is not arbitrary, but must go to 0 when n goes to infinity. But in such a way that n sigma squared remains finite. So this is a very peculiar situation, which is the one which Boltzmann considered. Now, okay, now instead Enskog, in his 1921 paper, considered the other limit in which n sigma cube remains finite. So these are two different limits, okay? But in both cases, the infinite classical dynamical system was considered. Now, keep in mind that in both cases, the theories are asymptotic. Namely, when you take the limit in which n is very large, namely epsilon is very small, you drop something. You forget some contributions which are infinitesimal in epsilon. This is a bad idea. So we have to understand that both approaches, but we now focus on the Boltzmann approach, are asymptotic. Okay? So in any case, from the two equations, the two kinetic equations, look similar, the Boltzmann and Enskog kinetic equations. They have the same form, apparently. You have a streaming operator, free streaming operator on the left-hand side, which is basically the time derivative, the Lagrange time derivative of the one-body probability density. And on the right-hand side, you have an integral differential operator or interval operator. In both cases, actually, it's an integral operator, which is called Boltzmann collision operator or Enskog collision operator for the two equations. I mean, this is very simple type of equation. Apparently, of course. I mean, the details are contained in these operators, which are different in the two cases. Okay, now. The situation is that they both consider this kind of asymptotic orderings different among the two cases, which means that we expect that their corresponding equations, I mean, Boltzmann and Enskog, must be asymptotic in some sense, approximate. Okay. Now, in both equations, in principle, are usually invoked to justify the second principle of the thermodynamics. In fact, the starting point, the reason why this justification is usually believed to be possible is based on the concept of Boltzmann-Shannon statistical entropy. Originally introduced by Boltzmann, but whose physical interpretation, theoretical interpretation, has been provided by Shannon. Shannon is the one who invented the information theory. And he found out that the Boltzmann entropy can be interpreted as a measure of ignorance on a dynamical system. Ignorance on what is the state of the dynamical system. So, for example, it is possible to introduce the notion of statistical entropy, Boltzmann-Shannon entropy, for the one particle kinetic distribution function. Now, and this is a famous Boltzmann-H theorem, which tells that the time derivative or entropy production rate associated to the one-body Boltzmann-Shannon entropy is satisfies this inequality. Okay, not only, but that this quantity is zero, the entropy production rate vanishes if and only if ρ1, one-body PDF, coincides with the Maxwellian distribution function. So this is a Boltzmann-H theorem published in 1872. It's a famous paper which I mentioned before. Now, okay, now we are going to now, the important fact is that in the Boltzmann paper, he assumed, he basically assumed that the one-body PDF could be an arbitrary distribution function. However, at the time in which Boltzmann wrote his paper, distributions, namely generalized functions, were not yet known. In particular, Dirac delta was not known. And so actually, the Boltzmann inequality, this fails in the case of distributions. Fails in the case in which rho 1 is the Dirac delta. And there are reasons, fundamental reasons, why we should include the Dirac delta among the possible solutions. Because you see, when you consider the probability density associated with a dynamical system, you must admit, you must allow the certainty, the certain distribution function among the solution. Namely, you must allow that the possibility that you know deterministically the state of the system. If you know deterministically, if you measure the state of each particle of the system at the initial time, you know that at all times you will be able to determine the state by solving the equations of motion, which means that the one particle distribution function must be a Dirac delta. Dirac delta pointing to the state of the particle at a given time, at the current time, the present time. So Boltzmann theorem fails for this reason, because it cannot apply to Dirac delta. It cannot apply to distributions in general. But of course, there is another problem. Another problem is what happens with mixtures, with fluid mixtures, when you have subsets of light particles, which differ for some features, physical properties like mass or diameter of the particles. But you can also have charged particles, of course. So in the previous paper, which I presented last Friday, in fact, we have considered the case of hard spheres which carry also a charge. A charge density constant on the surfaces. And it was also considered the case of relativistic particles. So the problem we are considering here is not relativistic, because Boltzmann theory is not relativistic. But can be set also in the special relativistic framework, or if you like, the general relativistic one. Okay, but anyway. So this is a much more general problem which arises also for relativistic particles, and it's very interesting to describe relativistic plasmas, for example, namely ensembles of charged particles. Okay, now the second principle has been related to Boltzmann H theorem simply by identifying the thermodynamic entropy with the Boltzmann-Shannon entropy. Okay, because the second principle tells us that pursuit of dynamical systems, pursuit of thermodynamic systems, I would say, the entropy inequality must hold. And these are typically isolated systems. So, but it is not always true that the entropy is conserved, the thermodynamic entropy. And therefore, it is questionable in principle to identify this quantity with the Boltzmann-Shannon entropy. But, you know, some people try to do so. So the serious problems with the Boltzmann-Shannon entropy is that, of course, as I just said, the Boltzmann H theory does not hold for all parts, for arbitrary probability densities. And second, both equations, kinetic equations by Boltzmann and H are asymptotic. It means they are not exact, okay? Because they are correct up to infinitesimals. You know, so we should keep track of these infinitesimal contributions. We can't neglect them in principle. Additionally, the H equation has a problem. It is purely phenomenological. It is not derived in a systematic way. And in fact, as Professor Dr. Gatignon pointed out, the S-block equation fails in the case of mixtures. I mean, that's what satisfies the Boltzmann, even the Boltzmann-English theorem. In the case of ordinary function, ordinary distribution functions. I mean, distribution functions which are ordinary functions. Okay. Now, this topic has been investigated mostly by mathematical physicists in the last 40 years, particularly. And most of the effort have concerned the so-called Boltzmann gradient. Namely, mathematicians and mathematical physicists have tried to find out if it is possible to prove that the Boltzmann equation becomes exact in some limit. Okay? This is a conjecture posed by Harold Grab, is a famous expert in kinetic theory, and who lived until 1987. And he suggested to this problem to the mathematical physics communities, maybe to look for a possible exact limit for the Boltzmann equation. Because the Boltzmann equation is asymptotic. But, he said, it might exist a particular limit, asymptotic limit, in which this, maybe if you let epsilon, a small particle, 1 over n, go to 0, he said, maybe the equation becomes exact. Okay, now, and this is a very, very important problem, which is basically unsolved up to now. But there is another way to overcome the problem. Let me consider the case in which both n and sigma remain finite. Because in this case, you don't have any approximation. So, the wisest thing to do is probably this, much simpler. Take n and sigma finite. Not take any, avoiding all asymptotic approximations. Which is better? So this is what we are going to do. Okay, we are going to keep n and sigma finite in both cases. Okay, so there are several motivations which should be mentioned, and in particular, if we are able to prove a weak H theorem, okay, similar to the Boltzmann one, without any approximation, without any asymptotic approximation, this kind of theorem will also be useful for a variety of different situations, like relativistic systems, So for relativistic kinetic theory, we believe that the same approach will be possible. So let us consider the case of a non-relativistic system. So we have an n-body system of interactive point particles, which we identify with a system of hard spheres. So the hard spheres interact only when they have collisions. And collisions are instantaneous and are elastic collisions. So assume that for the moment that we have only one species of hard spheres, namely they have the same diameter and the same mass. Then we shall consider the case of different species. For example, they might differ because of the mass or because of the diameter. Okay? So this is our dynamical system. The governing equations are given by the ordinary differential equation of first order. X is the state of the particle, or each particle, or in this case for n-body system. R is the configuration vector, the ensemble of all the position vectors, the center of masses for each particle, and is the velocity of the same center of mass. And so we have an ensemble of subsets of like particles in general, as I said. Okay, so we have well-defined set of equations of motion. Okay, and for this dynamical system, we set up the statistical formulation, the admonition. which means that if we introduce the n-body probability density in the phase space of the system, this will satisfy this differential Liouville equation. The differential Liouville equation is, if you want, the starting point of our formulation, statistical formulation. This gives defines the so-called microscopic statistical distribution. Okay. Now, if we consider our dynamical system, a fundamental property of this dynamical system is that this vector field X is divergence free. I mean, it is conservative. Now, this property is of fundamental importance, because we are going to prove that thanks to this conservative property, we are able to prove that the Boltzmann-Shannon entropy associated to rho n is constant. Okay, so this is a Liouville equation, okay, and this is a conservation property. Now, let us introduce the S-body reduced distribution function. This is a K-body. So it's simply obtained by integrating the n-body distribution function on the phase spaces of the remaining particle, S plus 1 or K plus 1, in this case S plus 1, until the nth particle. So we integrate on the phase spaces of the remaining particles. What is left is what we call here rho K, the K-body reduced distribution function, probability density. Okay, so we introduce also this quantity, which are well defined, and okay, and now we define introduce the concept of K-body, Boltzmann-Shannon entropy, for K equal ranging from 1 to n. And this is the same definition used by Boltzmann, but in the case of K equal to 1. Okay. His definition applies for the K when K is equal to 1, but it also differs from the sign, but the rest is the same. The reason why we are assigning minus is because we want the inequality, the Boltzmann inequality to be larger than 0, otherwise we have the risk inequality given by Boltzmann as an opposite sign, but conceptually is the same. But the Boltzmann-Shannon entropy must be defined with this sign here. I want to stress this definition contains the logarithm. Now, the logarithm is a function whose argument must be dimensionless. Okay, so we must be careful on this definition, on interpreting this definition, because it means that if the quantity inside must be dimensionless, we must introduce a set of measurements. But so basically, here it is understood that there is a constant which depends on the system of units. Okay, this is an arbitrary positive constant. Okay, so this definition actually contains an arbitrary constant in the argument of the logarithm. Okay, but clearly it is obvious because the logarithm can only be defined for dimensionless functions. Okay, not for dimensional like in the physics, because the distribution function probability density has dimensions, of course. Okay. Okay. Let me set this important feature of the Boltzmann-Shannon entropy, which is defined up to a constant in the logarithm. We now prove this very simple constant H theorem. And this constant H theorem is an immediate consequence. Of the conservative property of the vector field, which characterizes the dynamics of the dynamical system. In fact, let us evaluate the partial derivative, for example, of the n-body Boltzmann-Shannon entropy, and prove that this is 0 identically. In fact, if we differentiate the Boltzmann-Shannon entropy under the integral, it just we have this simple identity. And if we now invoke the Wheel equation used before and integrate by parts, we have to perform integration by parts, we are left with this representation. And now it is immediate to show that this quantity vanishes when you have the conservative condition, when the conservative condition holds. Therefore, both the microscopic Shannon entropy associated to the n-body PDF is always conserved, okay, for our dynamical system. Okay. Now we come to the Breuer lemma. Breuer is a theoretical physicist who had also some interest in statistical mechanics. In 1957, he published a book of statistical mechanics in which he presented this elementary result. Now consider Gn a strictly positive function, defined such that it is normalized to unity on the n-body phase space. And assume that this entropy integral exists. So we assume that Gn satisfies these two requirements. This is equal to 1 and this integral exists. Then it is possible to prove that the following inequality holds. This integral, which enters the n-body probability density, then n-body Boltzmann-Shannon entropy, is larger or equal to the other one. So if we replace Rn with Gn in the logarithm, we have this inequality. Now, the proof is elementary and follows from very simple arguments. So we can see the proof in detail. Now, if you consider the logarithm, this logarithm, it is very easy to show that this inequality holds. This is a fundamental inequality for the logarithm. If you tend to expand this argument around unity, then you have this majorization. Now, if using this inequality, then you have that the logarithm of the function g can be represented or can be is less or equal to the sum of these two quantities. Basically, it is the logarithm of the product, and this can be using this inequality gives this inequality. So this inequality is the one which was pointed out, the very simple one pointed out by Breuer. Okay, now, using this inequality, the Breuer, the preliminary inequality, then it follows the integral inequality in elementary way. But A is the difference between the function g and rho, so its integral is equal to 0. So this is equal to 0, and what is left is the inequality which we have pointed out at the beginning. So this is 0 automatically. This is a very elementary inequality which permits us to prove, first of all, the H theorem for weak H theorem in the case of the one-body PDF. Namely, based on the, let us consider the case of one set of light particles only. Then we intend to prove that this inequality holds. Which means that this quantity is the n-body entropy. This quantity is a one-body entropy. Okay? So this means that this inequality holds. So remember, Sn obeys a constant H theorem. But if this inequality holds, of course, S1 will satisfy a weak H theorem. Namely, it follows that the time derivative as 1 is larger or equal to 0, so automatically. So this is a weak edge theorem for rho 1. Now, this is obtained in the following way. Let us identify Gn as a product of rho 1. Remember, okay, this is the situation. We have two possibilities. We can consider the dynamical system formed by point-like particles or extended hard spheres like the Boltzmann-Sinai dynamical system. So this version of the proof of this inequality now consider the case of interacting point particles. For example, let us consider interacting point particles in which the interaction is electromagnetic, electrostatic, whatever you like, But the only requirement is that this the vector field x must be conservative. That's the only requirement. You have all possible interactions which you would like to consider, but consider only point particles. So this holds all F for all dynamical systems. Then you have this quantity. If you have point particles, then a possible choice for Gn is just the product over 1. And then you have the inequality, this entropic inequality, which of course, in the case of like particles, the summation is, of course, on terms, contributions which are independent of the index I, because the particles are all equal, are like particles, which means that this theorem holds, namely this inequality holds, and therefore the theorem, the weak theorem. Okay. So if we have point particles interacted by conservative force, this is always the case. Now, the Briolet lemma, however, can also be applied to the case of extended particles, namely the system of hard spheres, namely the Boltzmann-Sinai classical dynamical system. And the reason is the following: that you can you still have the inequality as the one indicated before. So the weak edge theorem applies also in this case. So this is a fundamental remark. We can apply the Boltzmann Briolet lemma also in the case of extended particles. Maybe it is trivial, but I want to stress this again. Now let us consider the case of unlike particles. Okay? If you consider this case, let us assume that you have only two species, species A and species B. Okay? And now the claim is the following: we are going to prove that both inequality hold, namely, if rho 1A is the one body probability density for species A, and rho 1B, the corresponding probability density for species B, the other species, we are going to prove that the one body entropy in both cases is larger as a production rate which is larger or equal to 0. So we are going to prove both inequalities simultaneously. Namely, we are going to prove that the weak edge theorem holds also for mixtures. Remember, and this must hold not only for point particles, but also for extended particles. Now, the proof is elementary. In fact, consider the case in which you have two species, A and B. Now, for the species B, the distribution function, the function G, which is used in the Briolet lemma, can be constructed identifying for the species B the quantity as a product of Maxwellian distributions. So basically, this is it, to be clear. Let us identify the trial function G, which enters the Briolet lemma, as follows. Is a product of the function ρ1, one body PDF for the species A. Instead, for the species B, we take Maxwellian distributions. I mean, strictly positive ordinary functions, which are Maxwellian distributions. Now, if these quantities are arbitrary, and remember, the logarithm in the entropy, in the Boltzmann-Chernow entropy, contains an arbitrary constant. Now, it is easy to show that the following inequality holds, namely the contribution of the species B vanishes. We can select, we can construct this Maxwellian distribution for the species B in such a way that their contribution to the entropy vanishes identically. It is a trick. Of course, it is a trick. And then as a consequence, we have this theorem. Now, changing the two species, A and B, of course, the same conclusion holds for the species B. Simple, very simple. Now, to reach the proof, we are using simply a suitable choice for this what we call trial function. And we are also using the fact that the Boltzmann-Chernow entropy contains an arbitrary constant, arbitrary positive constant. And that is necessary, of course, to take into account. So, anyway, the basic consequence you see that we are able to satisfy this constant. If we are able to satisfy this constant, then the conclusion is reached. And the reason why we are able always to satisfy this constant is that this logarithm actually contains an arbitrary constant, which you can select such a way to satisfy. The integration can be performed analytically, by the way. It's brilliant. So there is no difficulty. You can select a Maxwellian in such a way that we really perform everything analytically. So you get an equation basically for the temperature of the Maxwellian, which you can solve, provided, of course, there is a suitable constant here in the logarithm. Okay, so this is it. And let me stress again, this holds for arbitrary point particles and also extended particles. So what can we do? What more difficult? So and of course we are interested also in relativistic systems. So we expect the same result to hold in on relativistic kinetic. Okay, so this is it. And this motivates us because we are interested, of course, mostly in relativistic theory. For astrophysical plasma are potentially most of the time relativistic, but the viewpoint of the observer, of course. But you know, we are relativistic simply because the temperature are relativistic, not because the velocity, particle velocity are relativistic with respect to the observer. So there are many interesting applications, but here we are also answering to the old problem. Can we be consistent with the second principle of thermodynamics? Yes, why not? Why not? But careful. If we take the Dirac delta, if ρ1 is deterministic, that will be 0. We expect this to be 0. So it means an obvious conclusion. If we describe deterministically our system, of course the entropy will not change, will always be 0. 0 forever. But if we describe statistically, if we have a statistical description, then this is largely equal to 0, and this is consistent with thermodynamics, with the second principle. There is no approximation, nothing. This is just rigorous, elementary, very simple, and I hope you like it. But if you don't, that doesn't matter. Because this, you know that there are truths which are only personal. You know, from the logical viewpoint, there are sentences that are true, false, or undecidable. And typically, the taste is personal, so it is undecidable. I cannot criticize you if you don't like it. Okay, this is it. Thank you for your question.